All of this just to tell you that today will be about transistors. Hello people, and welcome to the third week of Sensors and Devices course. Today, as I showed you before, we are going to talk about transistor, and we are talking about miniaturization of those transistors. When we talk about miniaturization, naturally the first sentence should be there is plenty of space at the bottom. This was said by Feynman. I really recommend this book because he was a really interesting person. Read this book, it's quite funny. Let's start with Moore's law. Moore, working at Intel, said that the number of transistors per square inch was doubling every year. And since the 70s up to now, it's actually working. It's pretty linear, and every year we are doubling the number of transistors per square inch. If this will go on, that's to be seen, but so far it has been pretty linear. And why we want more transistors? That's probably the main question of today. And one reason, obviously, is for getting better video games. I'm relatively old, so I've seen most of this, of the Moore law. So I started playing games like this. And this is a game from '82. And if you flip the box and check what it's written here, I will flip it now. You can say that it says thrilling new graphics. Now, thrilling new graphics in '82 meant this. Now we are in 2020 and we have games like this. So 40 years later, this is what it looks like.
To do this smart.
And just by this, you can see in 40 years how much we have achieved in terms of number of transistors and power of computers. But let's go with order. So, what is a transistor and what is a bit, first of all? So, a bit is a transistor that can change state between 0 and 1. This is a bit. Then we have a byte, that in this case it's 8 bits. So, each single of those bits can change between 0 and 1, and this is an 8-bit system. So, 1 byte is 8 bit. If I have an 8-bit system, it means that the number of things that I can store, or the number of variables, are 256. That's the same that you can use in Arduino. So that one, it's an 8-bit system. So I can use 256. If you do a little bit of math, you can check why we can have 256 variables using 8-bit. Done already? And we want to decrease the size of the transistors in such a way that we can put more transistor in a small volume. It means that I increase the number of memory that I can use, and the product size is going to be smaller. So I can have more transistor in a smaller volume. It also means that the gate size, we will see it later, is shorter. It means that the electron speed is faster because now it's going to be a shorter path. And it means that the computer will be faster. So the switch between 0 and 1 is going to be faster. So faster computer. How to switch between 0 and 1? This is what a transistor is. In the book you can see that this is similar to a faucet. So you have a gate, the gate will control the flow of water. And that's the same things for a transistor. So in a transistor I have a source, I have a drain, and I have a gate that can control the flow of electrons. Probably it's better shown here, but I'm also showing you right now on the paper. All right. So, how does a transistor work? I want to have my source and I want to have here my drain. And naturally the flow that I want is in, let's say, the flow that I want is in this direction. So I want a flow of electron going in this direction. And I can do this if I'm using a gate. So I'm controlling the gate. When I turn on the gate, this can happen. If I turn off the gate, this is not going to happen. This is the basic of a transistor. So it means that this is the transistor size. So this is one transistor. So if I can manage to squeeze this one, then my transistor will be smaller. This is the size that I want to shrink. This is one point. The other point is I need all connections. So those one are all cables that needs to go somewhere to be controlled. So the main problem is if I have 2 billion of those transistors, it means that I need to have all of those cables going somewhere. Can you think a way of how to make those those connections better? So let's say that I want to control 6 by 6 transistors. No, that's maybe too complicated. Let's say that I have 9 transistors, so I have 3 by 3. No, this is too easy. Let's say that I have 4 by 4 transistors. So let's say that I have 6 in transistor. Can you get an idea on how to connect those one just by using, let me see, 8 lines? If I'm correct, I should be correct. We will see later. Coming back to the first transistor ever, this is the first transistor ever. This was invented in Bell's laboratory in 1946, and you can see how big it is. So the humans there are for scale. This is a single transistor. Only one transistor can switch between 0 and 1. In the last few years, we have reached chips with 40 nanometer, 7 nanometer, and 5 nanometer distances. And in a single fingertip, you can see there, you can have billions of transistors. This is how fast the field moved from the first transistor up to now. How to make them? If we take a look at this very sexist advertisement from Intel, the first thing that you need is a clean room. And you need a clean room because those transistors are so small that even a single grain of dust will interfere with your transistor, and then you have to throw away everything. You start with silicon. You have this huge chunk of silicon, and you start cutting it in small. Wafers. I should have a wafer here. I do. This is what a wafer looks like. It looks like this, and you can see the reflection of the camera. On this wafer, what I want to do? First of all, I want to oxidize. So I want silicon oxide on top of the wafer. Then I want to add the photoresist, and I want to photocure this photoresist on top. So I will use a mask, and then I will use UV for photocuring this resin. And this is exactly the same how 3D printer works. So how the resin 3D printer works. If you remember, I have a liquid resin, I have a mask, and then I have a UV light. This is exactly the same things, but on a very smaller scale. There are positive photoresist and there are negative photoresist. Can you guess which one is the difference? Maybe. We will see. Once I have my photoresist, I can etch my silicon oxide layer from top. And at this point, I can dope the silicon wafer or the silicon open parts with a dopant. so something that will be conductive. And then I will have my metal deposition, so I can make my connection between the source and drain and the gate. Those one are my connections. Now, if you manage to see here, but probably not, maybe I will change lens and I will check if we can see it with the new lens. See you now. Let's see if we can see it from here. Where is my spaghetto? Here is my spaghetto. You can see that some of them are broken, and this is why it's at my place and not at university. This one is broken. This one, it's still pretty okay, so I cannot see any scratch or any broken line. Let's see if we can see this. Still nothing. Let's try with another lens. This lens should be enough. It is enough. So those one are 150 microns times 50 microns the empty space. So you can see the different lines. As you can see, those one are the destroyed one. Another destroyed. And this one is still pretty okay. It's 150 microns times 50, and you can see. Okay, come on, focus. You can see also a little bit of dust here, actually quite a lot of dust. This is what lithography looks like on a silicon wafer. Then in all of those steps, which one will be the limiting step? Which one is the step that say I cannot go below this micrometer or nanometer size? What can you think? Because at a certain point I will have a limiting step. So I cannot go below, let's say, 22 microns. Let's say 22 nanometers. Let's say 40 nanometers. Let's say 7 nanometers. The limiting step so far is the wavelength. So if I'm using UV, my wavelength is roughly 190 nanometers. So it means that I cannot go below 100 nanometers. The wavelength of the light is not small enough for reaching features of less than 190 nanometers. Naturally, I can use different light sources. So if I use, for example, the extreme ultraviolet, which is now being standardly used, then I can reach 10 nanometers. And this is more or less the standard nowadays. I can go even lower than that, but then another problem that I will have is interference. So if I have interference and I have two features very close by, I will have interference and I'm photocuring something else on the plate. Same things with all the scattering properties that you have in the resin. So when I'm using a light and this light is passing through the resin, I will have backscatter, I will have internal scatter, and I will have a lot of problem with scattering inside the resin. So I'm curing something that I don't want to cure. This was first solved using a water immersion lithography. So I'm using now I'm using a microscope and I have an immersion objective and I can reach 30 nanometers using this method. 10 years ago, Intel presented the first 22 nanometers chip. Those ones are smaller than obviously 30 nanometers, and this was pretty huge step forward. The problem of those transistors is that you have a limited space. So Intel said, I can do better. Instead of doing bidimensional chip, I can go for three-dimensional chip. At this point, the internal part, so the part that is between the source and the drain, it's a fin. If it's a fin, three-dimensional, it means that the source and the drain are closer. It means that the the switch is faster, it means that I can pass electron faster, and I have more surface on the interface. And the gate is all over around. You can see in those two videos of Intel how they managed to reach the 22 nanometers and now can reach the 40 nanometers. At a certain point in the past, when we reached the 30 nanometers, they say, okay, it's impossible to go below this. Intel did first the 22 nanometers, then the 14 nanometers, then today they are selling the 7 nanometers. And the iPhone that will come out probably in this month will be 5 nanometers. 5 nanometers for silicon, it's impressive. You need to think, size-wise, that 1 nanometer are just 6 atoms of silicon. So having a chip that is 5 nanometer, it's pretty impressive. When I show you this game, this one was for the Atari 2600, and this was 3500 transistors. Nowadays, you have 20 billion transistors in a single computer, or even on your cell phone, billions of transistors, and something that is super small. And think that the Apollo mission that put man on the moon was using a computer with more or less 1,700 transistors, just for giving you an idea about number of transistors. Same thing works for memory storage. Memory storage works more or less in the same way. You still have a bit, you want to move it from, you want to switch it between 0 and 1, and you want to store that information. The first hard drives were 5 megabytes, and you needed an airplane for moving them from one place to another. Now we have small portable hard drives with 1 terabyte or more that can just fit in your pocket. And also, that's because we are switching from magnetic disk, in which we are using a magnet for switching between 0 and 1, to solid state hard drive or solid state memory, like the RAM works in your computer. And it's exactly the same of transistors. This one was top-down approach. So I'm removing part of my silicon for reaching those small transistors. Another way is to use a bottom-up approach. So, for example, I can have a polymer that can be either in crystalline state and in an amorphous phase, and I can use this transition for setting up my transistor. So I can say, if it's in amorphous, it's 0, if it's in a crystalline, it's 1. And now I can go down to molecular level. Another approach is to use carbon nanotubes. So, for example, I can use a single carbon nanotube for connecting the source and the drain. Or another way is to use a carbon nanotube that can be controlled by the gate. So if now I'm giving power to the gate, I can bend the carbon nanotube, and this one will make contact between the source and drain. And this gives us also another important idea, and is how to make and how to use micromechanical systems. Those are generally called MEMS. For example, I can have really small thermometer using lithography and checking the difference of resistance between different wires. I can have chromatography. I can do chromatography in something that it's smaller than 500 microns. I know how to make those because I use exactly the same technology that I use for making the silicon chips. I can have cell manipulator. Again, using the same methodology that we've seen here, I can make a lot of different mechanical parts now. Those, for example, are gears of 50 microns, and again, they have been done using the same technology. One interesting point of this technology is how to make gas sensor. In gas sensor, most of the time I have one metal rod, and I'm checking either the voltage passing through or the resistance of the wire. If some metals goes on top of this wire, then either the voltage or the resistance is changing. And I can monitor the change, so I know that some gas are present in the environment. This is how smoke detector works. This is how carbon dioxide detector works, carbon monoxide. Most of the gas sensor works using this principle. Now that I have the lithography for making very small actuators, I can also go extremely low for gas sensors. And this is one example using a single carbon nanotube in two electrodes. So I have my source and my drain, and I can check the voltage through. If some gas go through the carbon nanotube, I can detect it. And this is almost at molecular level. And this is smaller than a single coin. You can see here, the chip is only for making the connections. So extremely small, but super useful for gas detection. Another very important thing, because now we have seen how those carbon nanotubes can be used for gas, but I can also chemically modify the carbon nanotube. So if I chemically modify a carbon nanotube, for example, with a single strand of DNA, and when a molecule or a protein goes to attach to the DNA, I can detect it just because I'm using those two electrodes. Same things in this other example. I now put a thrombin aptamer, which can be recognized by a thrombin, which is a protein. So if I'm flowing the protein through, it will attach on the carbon nanotubes, and I can detect this single attachment on top of carbon nanotubes. How to make those sensors? It's again the same things that you did during the first course. It's just microcontact printing those carbon nanotubes on top of the surface and putting the two electrodes nearby. Pretty straightforward, but then you have multiple carbon nanotubes. This is not a single carbon nanotube. As we are in 2020, I would like you to read and study this paper. In this paper, they use single carbon nanotube and they modify it with receptor for a virus. Then when you flow a virus on it, you can detect the single attachment on the virus. I can show you here. You probably cannot see this picture on this slide, but the slides will be given to you. This is a virus that you can see because it was tagged with a fluorescent molecule. Is moving near the carbon nanotube. It touched the carbon nanotubes, so you have a decrease in conductance, and then it's going away. So the conductance goes back to the standard baseline. Then another one is coming in, is touching. Again, you see the conductance going down, and then it's going away. So in this method, using one single carbon nanotube, you can detect the presence, the attachment of a single virus. And this is impressive. For today, it's all. That's the third week, so we are halfway, and I think you deserve a pizza. P.S. In the previous video, I showed you how to work with the breadboard, and I told you that historically they have this split part here because it was used for transistor. At that time, I didn't have a transistor. This time, actually, I have a transistor, so I can show you that this one fits perfectly in the middle. This means that those lines are not connected with the bottom line, and I can use each single line for programming my transistor. Just a fast update. See you tomorrow.